Okay, chapter 17 begins with current, just defining what current is, and then we're going to look at the two things that affect current. Now, before we get into this, chapter 17 is extremely short. It's a very quick chapter. You can do the homework set in one sitting probably. Sit down, start working it out. Before you know it, you're done. 17's easy. It's the warm-up for chapter 18, which is where you're going to have more involved circuitry problems. You're not going to be able to do chapter 18 in one sitting. Okay? All right, so chapter 17 begins with the definition of current. Current has the symbol I, and it's defined as charge over time. Now, what do we measure charge in? Coulombs. What do we measure time in? Seconds. A coulomb per second has a name that you probably have heard. Not a watt, an amp, which is actually ampere, A-M-P-E-R-E, but who adds the E-R-E? Nobody really. Technically it should be there. It's just amp. Coulomb per second is an amp. All right? Now, current, as with all things in physics, is based on little positive charges. It's based on positive charge motion. When you think back to the electric field, how did we define the electric field? The electric field was the direction that a little positive guy wants to move. In chapter 16, when we defined electric potential, you have 2 points in an electric field. Which point is at a higher electric potential? It's based on a little positive guy. So now here we are in chapter 17 talking about current. The direction of current is defined as the direction of positive charge motion. So here I have a real simple circuit, a battery with a light bulb. So I want you to imagine you became microscopic and you could climb inside this wire and you see a positive charge in there. Which way will this positive charge want to move? Is it going to move towards the positive terminal of the battery, or will it move away from the positive terminal? Away. The current flow is going to be like this. The current flows through the wire like this. Positive charge motion, which I want to mention right now. This is weird because in reality, if you hook up an electrical circuit, what actually moves through the circuit? Electrons, which are negative. So yes, I've been teaching this long enough where I know that even after I go over it, somebody's going to ask me. They're going to say, Spaldo, so in reality, don't electrons move through the wire? I'm like, uh-huh. So why is current positive charge motion? Well, it just is. Everything in physics, when it comes time to make a sign convention, which way are we going to define the electric field? Positive charge motion. Which way, which point has higher volts? It's based on positive charges. Which way does current flow? It's based on positive charges, And it's really confusing because in reality, do positive charges even move? No, they're in the nucleus, right? They're not free to move. The electrons are. It don't matter. We're going to say positive charge motion is current. All right, so here's a question for you. So if the current in this circuit is 5 amps, how many electrons pass through the bulb in 1 minute? So you're going to be using the definition of current. Oh, and you also have to know something about an electron. The charge of an electron is 1.6 times 10 to the negative 19 coulombs. So if the current flowing through this bulb right here is 5 amps, how many electrons will be passing through the bulb in 1 minute? So I'll give you, take 1 minute, figure this out. Okay, so what you do, take this equation, take the definition for current, solve it for charge. So charge is going to be current multiplied by time. So we got 5 amps, which is 5 coulombs per second. 1 minute is 60 seconds. The seconds cancel. So we are talking about 300 coulombs. Now, how do we convert 300 coulombs to electrons? Well, one electron has a charge of 1.6 times 10 to the negative 19 coulombs. The coulombs cancel, and we get 1.9 times 10 to the 21st electrons. Right? That's a lot of electrons. Okay, that's a pretty common question. You know, it's just a conversion. All right, next thing. Circuit diagrams. Now, from here on out, so I just showed you a circuit that was kind of set up like this. This is not how you want to show a proper physics circuit diagram. Definitely don't do this on the AP test. You don't want to be like, okay, here's a car battery. You know, like you open up the hood of your car, bam, there's your battery, right? That's not how you diagram it in physics. The way you draw a battery in physics, it's real simple. Long line, short line. This is your battery right here. The long line represents the positive terminal of the battery. The short line has a negative, is the negative terminal. Make sure you do long line, short line. If you do two equal length lines, that's a capacitor, which we'll be talking about later on. So long line, short line's battery. Now, resistors. So these are light bulbs. The most common resistor in a physics problem is a light bulb. Don't call them light bulbs. You're going to call them resistors. Why would we call these resistors? Of all things that we could call it, why would we call these guys resistors? What are they resisting? They're resisting the flow of charges, which is current. If you take the resistance out of a circuit, if you completely remove the resistance, you're going to get what we call a short circuit, which is a spike in current. You know, it's huge current. Okay, so you need resistance in a circuit to keep the current down, as we're going to see on the next screen. Okay, so all I want you to get from here is how to draw a circuit diagram. You show the battery like this. A squiggly line represents resistors. Okay, that's a circuit diagram. Oh, and then again, notice the direction of the current. To figure out the direction of the current, you got to look at the battery. So you look at the battery, and what you do is you put yourself in the wire and you go, which way would a little positive guy want to go? Well, a little positive guy wants to go away from the positive plate around to the negative plate. So that's the direction of the current. Okay? All right, Ohm's Law. Ohm's Law is the biggest equation of second semester. You know, for first semester, I would say the big equations were the kinematics. Would you guys agree with that? The kinematics were used and used and used and over and over and over. Ohm's Law is, I mean, you will have this memorized to the point when you're 30 years old. Even if you never take another physics class, you'll probably still remember Ohm's Law. So what Ohm's Law does is it relates the three important terms for a circuitry problem. It relates voltage, current, and resistance. Voltage, current, and resistance are the three key things in a circuit problem. Now, what I like to do when I'm first explaining Ohm's Law is take Ohm's Law and rearrange it for current. So it's the same equation, but just written in a different way. Current is equal to voltage over resistance. So look, what's going to happen to current if you increase, what happens to this if you increase the voltage? The current goes up. I think everybody would agree with that. If you have a stronger battery, you're going to have more current. Okay? Now, what happens to current if you increase the resistance? If resistance goes up, then what happens to current? It goes down. So it's a nice way to see, you know, the way you want to think about Ohm's Law is the two things that affect current are voltage and resistance. Okay? Now, here we have another circuit diagram. What was I going to say about this? Oh, This right here is grounding. That symbol there represents grounding. Grounding is the point where you have 0 volts, right? Now remember, when you talk about volts, the important thing is the difference between 2 points. If you see this symbol right here, if you see that on a circuit diagram, it is telling you at that point you have 0 volts, right? That's what that means. It kind of gives you a 0 point. And basically, grounding is where you have a circuit connected to the earth, you know. That's what that means. So let's see. I think that's it for here. Oh, one other thing, I haven't defined resistance yet. If you take Ohm's law and rearrange it, resistance is voltage over current. So this gives us units of volt per amp, and a volt per amp is an ohm. This symbol right here is referred to as an ohm, O-H-M, the symbol omega. So, you know, so for example, like right here, 6 ohms. What does 6 ohms mean? 6 ohms means 6 volts per amp. Now what does that mean? What it means is if you want to have 1 amp flowing through that resistor, if you want to have 1 amp in there, how many volts need to be across it? 6. So what if you hooked this up to 12? Ooh, look at that. It's 12 right there. If you hook this up to 12 volts, well, look at it. 6 volts per amp. We're hooked up to 12. So how many amps are we going to get? 2. Okay? All right. All right, last screen. All right, so Ohm's law. So we have a 6 ohm resistor connected to a 12 volt battery as shown. The circuit is grounded at the lower left corner. Grounding tells you the point where the electric potential is 0. So bam, right there at 0 volts. Okay, what is the current in the circuit? Now, guys, this is the easiest of all circuit situations. What makes this easy? The thing that makes this absolutely easy is notice we have 1 battery and 1 resistor. It doesn't get any easier than that.
I gotta run to the restroom. I'll be right back. I got an 8 here.
Okay. So we got 1 battery, 1 resistor, and we'll work up from here. But using this easy situation, I want to show you something. So remember last chapter we talked about how when you talk about voltage, notice this is delta V right here. When you talk about voltage, the important thing is the difference between 2 points. So if this battery is 12 volts, what that means is the negative plate is 0 and the positive plate is 12, right? Because what's the difference between 0 and 12? 12. Now, if you really wanted to, you could be like, 10 and 22, although hold on a second, this is grounded, which means that has to be 0. But anyway, it's the difference between the points. Okay? So look, here's what happens. The current here, so which way is the current going to go? You always start if you're figuring out the direction of the current, you start at the battery. So put a positive charge in this circuit. Let's say you put him like right here. Which way is that positive guy going to go? That way, clockwise. So the current goes like this, and then back into the battery like this. So here's how you think about it. The positive plate is 12 volts, the negative plate is 0. So how many volts do we have right here? 12. How many volts do we have right here? 12. Now, this side is 0. So that's the negative plate, that's 0. So we got 0 volts because that's grounded. How many volts do we have right here? 0. So look, how many volts are across this resistor? When you cross this resistor, you're going from 12 volts to 0 volts. So how many volts do we have? What's the delta V for that resistor there? Negative 12. So technically it's negative. The negative's not going to really matter here. I wouldn't put the negative there, but it is technically negative. All right, so what I want you guys to do is figure out what is the current in this circuit, and then what is the electric potential What do we measure electric potential in? Volts, right? What is the electric potential at point A, point B, point C? So take like, I don't know, 2 minutes. Yo. R is this, the 6. Yep. Okay, so take a couple minutes. So let's get my black pen back. So here's how you solve it. So first question, what's the current in the circuit? Shh. Current in the circuit. You take Ohm's law, rearrange it. I is delta V over R. So the voltage, look at the voltage across, because we're going to be using the 6 ohm resistor, right? The voltage across the 6 ohm resistor. So you start at the battery, right? If it's a 12 volt battery, that means positive plate is 12, negative plate is 0. So we got 12 volts, 12 volts, 12 volts, 12 volts. Those are all, that's the electric potential, right? Okay, now down here we got 0, 0, 0, 0, 0, 0. So notice that when you cross this 6 ohm resistor, you're going from 12 to 0. What's the voltage across it? 12. So this comes out as 2 amps. Now look, let me show you where you get amps from here, just so you understand it. Look, volts over ohm, look at what that really is. So volts over ohm, that's volts. Now what's an ohm? An ohm is a volt per amp. That's what an ohm is. So the volts cancel and you get amp. An ohm is a volt per amp. Okay, second question. What's the electric potential at, well, we've already answered this, point A, point B, point C. So look, point A is right here. The electric potential is how many volts you have at that point. What's the electric potential in this region right here? 0. Hey, wherever a circuit is grounded, wherever you see this symbol right here, that's the point where your electric potential is 0. They're telling you, you know, everywhere in here is 0. The only time your volts will change is if you cross a battery or cross a resistor. That's a good thing to make note of. The only time your volts will change is if you cross a battery or cross a resistor. Okay, point B is up here. How many volts do we have on this side of the battery? 12. And then point C, we're still at 12 because we didn't cross, you know, going from B over to C, we didn't cross a battery and we didn't cross a resistor. So it goes 0 volts, 12 volts, 12 volts. Those are the electric potentials at those points. Okay? All right.